So I think, yeah, we can start then. So today we'll look at a bit more in terms of deep learning only. Okay. So yesterday we had done a uh, very basic approach to what is deep learning. Today we'll go into depths of how to implement for neural networks. Okay, we'll look at forward propagations in a bit more detail, and we'll understand why neural networks are required. So yesterday it was more about what is a neural network, right? What is a small neural network? But we didn't cover whys, right? We didn't talk about okay, what is the problem with normal machine learning models that we need to go so that which enables which enforces us to go towards a machine learning or a neural network, deep neural network model. So today we'll look at those aspects, and then obviously we'll try to code up a forward neural network propagation kind of thing to understand like how a neural network works in detail. Okay. So let's go into the discussion. So let me share with you first of all again the OneNote on the screen. So I hope my audio video is clear. So I'll switch off the video soon once I start on the OneNote side of things. Setting things up, I'll just share my screen quickly. Just create today's details. So today we'll be looking at code also. Okay, today we'll be writing code also, and I'll encourage all of you to I will be sharing the notebooks and everything. So try to refer to the code, try to understand what is truly happening in the code, right? So that you get a better understanding of the machine learning models and deep neural networks. So yesterday's this OneNote page has been shared in the Google Drive. I think the ops team will work with you to on the drive location and everything. Do let me know if you have not received the details. I'll nudge them once more to share the details with you. Okay. So yeah, let's go into that. Let's go into the whys first and the hows in a like how do we do it in a bit more detail today, right? So okay, so let's go into that first. Then I'll pause for questions about yesterday or today, right? So let's say you work for a bank, okay, and can write it down parallelly and switch off the video first. So imagine you work for a bank and you need to I'll just type things up. So imagine you work for a bank and you need to build a model predicting, or you need to predict how many transactions each customer will make next year, right? Let's write it down. So bank use case, let's say, right? You can see my screen, right? So can anyone quickly confirm if the screen is visible?
Yes, it is visible.
Great, thank you. So we want to predict how many transactions a user does in the next year. Okay, very important from a bank's perspective because this drives revenue. This drives the running revenue of a bank, right? Because each transaction or each NEFT or each UPI, the bank receives some amount from the merchant or the user, right? Like if there is a credit card transaction, then some credit card points and things like that they have to process, right? In next year. So this is a very important metric that the bank wants to predict, right? Now, what we see, say, in a linear regression model, if you remember what linear regression does, it takes multiple factors into account, right? Say it will take customer age, right? So say customer age is A, then it takes, say, bank balance, right? So these are the different features that we talk about. So we'll have, say, 4 features, okay? Bank balance, then say it has like whether they're retired or not, kind of thing, right? So say I'll call it is retired, kind of thing. Okay. Then we look at and so on, right? So we'll get to deep learning in a moment, but for comparison, let's see how a simple linear regression model works for this problem. Okay. So the linear regression embeds an assumption that the outcome, that is in this case, how many transactions a user makes, is the sum of individual parts, right? So it says that whatever is the input, so it will try to take each of them and try to predict the transactions. This basically how many transactions a user makes in the next year, right? So this is what a linear regression model does. So it takes the three things and it will predict each of these things, right? Based on each thing, it will try to predict it, right? So it says basically, initially it says, okay, what is the, say, what is the average number of transactions a user makes? Then it will try to add the effect of age on top of it, right? Then it will try to add the effect of bank balance on top of it, and so on, right? So the linear regression model is not identifying the interaction between the parts, right? Or how they affect banking activity, right? So say we make plots for the model. So we have one line for, say, we have one line for this. The y is always the how many transactions, right? The x is all the, say, a, b, r kind of things. So we'll have a line for customer age, right? So this is just a relationship between the feature A and T. Okay, so it's a linear relationship. There is no. It can be like quadratic relationship, but it is on the 2D plane only, right? And it is one to one. Right? It is never like one to many or many to one kind of a relationship. Similarly, B will have some other relationship, right? Again, these two are not parallel, so they will have different relationships. So more the bank balance, more the number of transactions, or more the age, more the number of transactions till some point of time, right? So this is how the our algorithm, our predictions look like, right? So the problem with that is, like, these two graphs are not interacting with each other, right? So we are not trying to find out. So limitation of a linear regression model is, so limitation of a linear regression model will be uh, does not capture the relationships between the features, right? It does not capture the relationships between the features. So we are not talking about the issues that, okay, if the person is retired, maybe his bank balance is starting to fall, right? Or if the customer's age is more, that balance will be anyway higher, right? So we are not capturing the interdependencies between them. Okay. So yeah, and there can be other features also. Like I just saw in chat that someone has written professions. Obviously, there can be other features also. I'm just taking three features for now. Okay. So to add more features, we like to add interdependencies or interactions between the predictions from a model, right? Or between the features, we want to use neural networks. Okay, so neural networks are a powerful modeling approach that accounts for interactions like this especially well. Okay, so the focus of this course, that is deep learning, is the use of especially powerful neural networks, right? So neural networks basically take away this um, functionality. So neural networks no, overcome this limitation, right? And once they overcome this limitation, they what they try to do, they try to capture interdependencies. They try to capture relationships between features, right? So how do they do it? Okay. So yeah, so complex interactions, and not just in textual data, right? So complex interactions can also be in images, in videos, in audio, in source code, anywhere, right? So how do they do it? So say in this example, right? So you can understand that there is an interaction between, say, retirement status and bank balance, right? So instead of having them separately affecting the outcome, like in the linear regression model, in the linear regression case, it was separately affecting the outcome, right? This is affecting the outcome. This is affecting the outcome, right? But in neural network, what will it try to do? It will try to figure out the interdependencies between, first of all, bank balance and retirement status, right? So this is an abstract thing. Now you don't know what you will call to that interaction, right? What will you will call that interaction? So it can be anything, but it tries to find out some relationship between them, and then it joins it with age, right? And then tries to find the output, that is t, right? So this graphic, basically we are oversimplifying the reality, obviously, but here I'm just trying to show that many things interact with each other in some way, right? Obviously, age and retirement status also be interacting in some way, right? And that's where the interconnected nodes that we saw at the end of the yesterday's class, where I said, okay, I'll explain it in more detail tomorrow. So I think someone had asked the question like, okay, how do we actually train the model, right? So that's what we will look at today in a bit more detail. Okay, so this is what. So we are oversimplifying the reality here, but the diagram of a neural network will essentially look like this. Okay, so now if you have to think of like comparing, like having all the features, right, having all the interdependencies, then ideally it will look like this. Okay, and then which gives the final output, that is t, right? So you can write it here itself, t. Okay, so if you see this and these are exactly same, right? Why they are exactly same? Because if you made this equal to 0 here, this weight equal to 0, and this weight equal to 0, right? Then this input would have been a only. So this output would have been a only, right? Or some value of a, right? Some modification of a. If this was 0 here, if this input was 0 here, and this was 1, and this was 1, right? Then this would have been boiled down to, this input would have boiled down to b plus r, right? So this, the first image would have boiled down to the second image, right? So that is what a neural network is. So it will capture interdependencies between the data in many ways possible, right? So the weights, we can choose how to give the weights, right? Depending on either it can be domain knowledge, it can be in the algorithm, it can be in the optimizers. We'll look at that. But this is the crux of a neural network. Okay. So any questions here? Did everybody understand like how this model degenerates into this type of a easy, smaller neural network?
Okay, in the second one, is there a reason to get two nodes? Means when we are joining for first node,
Mhm.
what's the need for the second node? Means are we not joining the same stimuli?
Not necessarily. So if you see the weights in the first node, right? Let's actually, very good question actually. I think Vishal, right? I forgetting names. Um, okay, let me actually just change the color. See, if you see here, the stimuli in this was, for this one was the way, if I talk about the weights, for this one it was A1, that is this is equal to 1, right? B0, that means B is not providing a stimulus to this, and R0. R is also not providing a stimulus to this. So what is the total input here? it is A into 1 plus B into 0 plus R into 0. That is A only, right? For this one, which boils down to this effectively, which boils down to this. What about this one? This one, if you see, A is 0, B is 1, and R is 1, right? So what is the total? So even though we are using two nodes, the stimulus that we are applying to individual nodes are very different, right? And that we are determining based on the weights that we have, right? Based on the initial weights that are there, right? That is in our hands, because that is the W, that is the the parameters that we can determine, right? Because A, B, and R we don't have any control over. That is the data set. That is the data that we have, right? So now these two values actually are passing two things. So this is just passing A or some activation function applied on top of A. This is passing the B plus R or some activation function applied on B plus R. So we can call it, say, F of A, and we can call it F of B plus R, right? In this case, we were directly passing A, and in this case, we are passing F of B plus R, right, in the first place. So this and this are now very similar, right? So here, say the activation function, if it was nothing, if it was just equal to 1, right? Basically, we are whatever we are getting, we are just passing it out. Then the second complex neural network will boil down to the first, right? But if you knew that, okay, there is some interaction between, say, retirement and age also, right? Then obviously you could maybe have a third, you could have say a third node here, right? Where B would have been equal to 0, A and R would have been equal to 1, right? So all these types of complex interactions you can actually build with a neural network.
Okay.
Does this make sense, Vishal? Okay, great.
Okay.
Yeah. So this is what I was talking about when I said that complex interactions can be modeled on top of this, right? Yeah.
Sir, I have a question.
Yes, please go ahead.
Uh, so if there are only like two nodes initially,
Mhm.
so
Mhm.
the result is out already. I mean, like for the two nodes, the weights are calculated and the results are. So what if the other node is added? Will the entire neural network change automatically, or like we need to make some changes?
So you are saying that you had created a neural network with A and B features only, and now you want to add the R feature into the neural network?
No, sir, not that. But like A, B, and R is like initially there, but the relationship which you have established, right? So the next two nodes after A and B, the next two circles which you have drawn. So if there is a third circle which you are mentioning, like if it comes after the result, so we should make some changes, right? Or it will automatically make itself.
So in like when we look at Keras or PyTorch libraries and these things, you will see it will automatically handle that, right? You just need to change the number of nodes in that layer. So it will automatically recalculate everything. But yeah, the recalculation or the remodeling has to be done completely. So if you add a node here, right? Because the moment you add something here, this output will change, right? This input will change, right? Now it will have 3 inputs instead of 2. Or if there were other layers, other nodes also in the third layer, then the inputs will change, right? And that's why like the recomputation has to be done completely. Like you cannot incrementally build it if you add a new node into in one particular layer.
Yes, sir, got it. Thank you.
Yeah. So
Rajan?
Please go ahead.
Is it like we'll be having only one hidden layer or multiple hidden layers?
Not necessarily. I'll just come to that. Shruti.
Okay.
So we can have multiple hidden layers. This is just an example that because
Okay.
it is simple interaction. So we are just having one hidden layer.
Okay.
It's not
One more
necessary that
thing.
we will have one hidden layer. Yeah.
Yeah, okay. One more thing, this number of nodes, is it going to be like a hyperparameter tuning we need to find, or need to specific? Is there any way to interpret that one?
So number of nodes generally is thumb rule is the more the number of features, the more is the number of nodes, right? Hidden layers generally 2 or at max 3 helps. You don't need to have many hidden layers. It doesn't add value. We'll come to all those things, why it doesn't add value when we look at backpropagation, when we look at optimizers, so today and tomorrow. We'll come to that part, but number of hidden layers doesn't add much value incrementally. So after 2 and 3, it majorly stays there, right? It saturates. But number of nodes generally depend on the number of features. So if you have, say, if you're looking at an image which has, say, 512, or generally if it's a 8 cross 8 cross 8 image, it will have how much? 8 cross 8 is 64 into 8, right? So you will have 512 odd nodes, 512 odd features, or 512 odd pixels. Then the number of nodes will be much higher in the first hidden layer itself, because it has to calculate those many complex interactions, right? Or many more complex interactions, because it has to figure out corners, it has to figure out edges, lighting, shadows in an image, right? In pixel wise.
Okay.
So yeah, so contours. So in the like near the nose, a human being will have a contour, a height change, right? So all these complexities. So the number of nodes that you have in a particular layer, the more complexity you should be able to handle. Okay, that again, that there is an upper limit, but generally we see that it has to increase with the number of features. Here we had 3 features, so we add 1 or 2 or 3, more than enough. You don't need to add more than that.
Yeah.
Okay. So yeah, so as a continuation to Sruti's
Okay,
question,
also
so
this weightage, how we will be calculating? Like, is there any method to calculate the weightage or?
yeah, so the weightage part, we don't have to calculate. So what we do is, so we are currently looking at the forward propagation layer, right? We are not looking at the correction part. Correction means, so once we predict T, based on the actual output, these weights have to be corrected, right? So we will come to that. So it follows a very similar way of like gradient descent that we have in linear regression. And with gradient descent only, these weights can be tuned. So even if we don't give like exact weights, if even if we give random weights, that is what we do, because you cannot give manually weights to say 500 odd connections, right? So you will give random weights initially, but once the back propagation happens and once we look at the correction layer, you will understand that weights will automatically readjust themselves, right? So after 4 or 5 levels of forward and backward propagation, we'll come to why we need a backward propagation and how it works. So you will see that the weights will, like whatever you start with, you will find a good weight to end with at the end, right? So you don't have to worry about the initial weights or initializing the weights of the model, okay, of the parameters. So this is an example. That's why I put weights. And today the code that we'll look at there also we will put weights. But later when we actually look at Keras code, all right, how models are built in the production, then this is for explaining the individual parts. But then you will see that at that point of time we'll not need to put the weights manually, right? We'll say key generate random numbers and put the weights kind of thing. Okay, Deepika.
Okay.
Yeah. Any other questions? Cool. I think then no other questions. Great. Keep the questions coming. So let's move forward. So I think we have a very basic neural network up now, right? So if you have to build, say, this type of a neural network, right? So what we don't have right now, okay, what all we have now, first let's discuss. So we can quickly write the code for this one. So let me just set up the code environment. Give me one moment for that. I'm just sharing my Jupyter. I'm just starting up my Jupyter notebook. So we'll share the screen shortly again. So let me know again once you can see it. This generally takes a bit of time to render the Jupyter notebook sharing. Screen. I just created a notebook at in my local. I hope that this one is visible now. Right. So let's look at the code for this one. So what we want to do essentially is we want to create the inputs and the outputs, right? So let's try to do that. So I will just create, okay, I'll quickly explain like what I'm trying to do. So I'm say for now keeping two inputs. Okay, so I'm keeping two inputs. So I'll first create an array, a NumPy array. Okay, so I hope you can see my Jupyter notebook screen, right?
Yes, we are able to see.
Okay, great. So I'm just importing NumPy here, right? So I complicate. Done and edit. We have the shortcut for that. Alt enter. Yeah. So I'm importing NumPy and creating an input sequence. Okay, input data. So input data essentially is the three features that we talked about. I'll do it two only for now. Okay. So input data, it has say a NumPy array of two things, right? So of two things, say it has two values, so 2 and 3. Okay, just this is the input data. The weights that we have, and I'll explain like what type of a neural network I'm trying to build. I'll just add three weights for now. So weights will be say for now I'm keeping as a dictionary, and instead of like randomly allowing to choose weights, for now I'm hard coding the weights because I want to show actually how it works, right? So I'll say the weight for the first this thing, a first node is 1 1, and I'll explain what I mean by that. Then I have the second node that is, so I'll just copy these and write it and paste it 3 times. Right. So we have three nodes. So node 0, node 1, and that's it. Say the output node. Okay, so the second weights are say -1 1, and the third node is say 2 1. Okay, or 2 minus 1, whatever you want to keep, right? So I have the weights, and so if I let's do alt enter. Okay, some issue happened.
You forgot comma after to node one.
Yeah, cool. So yeah, so we have the weights. Okay, so how the neural network will look like. So what I'm trying to build essentially here is a neural network, something like this. So again, let me see if I can take insert an image here to see if I can enter an image here or not. I think in Jupyter I won't be able to. So I'll find the OneNote again. I want to share my full screen, but actually this laptop doesn't allow me to share my full screen, so I have to switch tabs a bit often. Just bear with me on that. Okay. So it only allows me to share windows, like each window at a time. So what I'm trying to do is trying to create a neural network, something like this. So we have say 2 3, and yeah, so I have 2 3 as the input layer. Okay, then I have 1 1. You saw that I had written, right? 1 1 -1 1, and then the output layer 2 -1, the weights, right? So that is how I'm assigning the weights. Okay, and then I'll have to just create the values, right? So if I have to just create the values, so how will it look like? I'll paste the code here also to explain, and then I'll write it on the Jupyter notebook to put things down. So I'm just taking the code from there and just pasting it for now here. Right. So what I'm trying to do is I have created the weights, right? And then so what will be the value of the node 0? So the node 0 value will be the input data, right? Whatever the input array is there, because both are coming here. So it will be a dot product, right? So it has to be a dot product. So if you see the input data is 2 3 and the weights are 1 1, right? So we have to do a dot product. So we have to do 2 into 1 plus 3 into 1, right? That is 5. So dot product is nothing but we make a product first and then we make the sum, right? So that's what we are doing here. You can see here, this is the dot product. So we are making the product first and then we are adding them up. So this will be the node 1 dot value. This will be this 5. So does it look correct, everyone? So I'll just, this code I've put in Jupyter, I'll just show it in Jupyter, the run. Okay. So this is how we are creating the forward propagation part, right? So now when we will print it, so one thing is missing here. Can anyone tell what is missing here from yesterday's class?
We didn't add
So what
bias.
we didn't add bias. Okay. Any other thing that is a problem? So bias
We
was
need
just
to
to shift
activate this node.
Exactly, yeah, Shruti. So we have to add the activation function. Otherwise, if all this big neural network will remain it's a linear thing at the end, right? We had seen it on the other day. So let's try to do the activation function part as well as the code part in Jupyter itself. Okay. So I'll share the Jupyter notebook and let's try to do it there only. Right. So everyone has made a note of this model, just this diagram, so that it's clear, so that like you can just take a screenshot of this for now and keep it on your side, so that when I write the code, it's easier for you to correlate. Okay, because that screen cannot be shown there. So I'll also draw it out. So I hope everyone has taken a small screenshot for this. I'll go back to Jupyter and I'll just write it like how it looks like, how our this thing. How our deep neural network looks like. So we had 2 and 3, and then we had two middle layers, right? So we had 2 middle layers. So we had, say, node 0. This is our node 0, right? And this is our node 1. And then the weights are already given here, right? And then we had output, right? So the weights you can see. So weights are 1, 1 from both the nodes, then it is -1, -1. And then from node 0 and node 1, the weights are 2 and -1. Okay. So this is the configuration. This just wanted to explain. So our node 0 value will be that I just pasted. It got undone. So the node 0 value will look like our input data into the, I'll just into the weights. So this is the dot product that we do, right? So when you do the dot product, you can also do np dot dot, right? You can also do that. So I'm just doing it here because I wanted to show in a bit more detail how it works. And I'm assuming that you like not all of you remember everything in Python that you have done. So I wanted to keep it like as simple as possible, right? You can also use directly dot product. That is perfectly fine, right? So this is node 0, and then you have node 1 value. So node 1 value will be nothing but input data into weights of node 1. So this weights is a dictionary, right? So this is a dictionary in Python, and this is the sum for that, right? So we have printed this. Okay. So node 0 and node 1 value we have now. So we can just look at what the values are. So we can just print the values here. So we have 5 and 1. Okay, so obviously 2 into 1, we had 5, we have 1. So we have the 2 middle layers right now, right? Next, what we have to do, we have to pass this to the next layer, right? We have to pass this to the next layer. So I'll just call it, say, hidden layer values kind of thing. Okay, I'll just call it hidden layer values to maintain uniformity, right? And I'll just call it np.array, the node 0 value and the node 1 value, right? So this is now the hidden layer values that we have. And I will just try to print the hidden layer values once more, just to see that if the things look good. Yeah. So when I print hidden layer values, something has broken. Oh, I forgot to do this. And that's why, like in Python, like if you're writing in Jupyter, always like try to print things and try to see, right? So you will get an idea of the debugging parts also. right? And then when we do what we have to do, now we have to go to the output layer, right? Now we have to take the hidden layer data into the output layer. So what will we do here? Anyone can tell what we need to do here?
We need to take the hidden layer values into the weights of output dot sub.
Correct. So we have to again basically now we have to calculate the output. So we'll take the hidden layer values and we'll multiply with the weight of the output, right? And we'll do a sum here. Okay. Okay. I think missed. The weight is not defined. This is weights, right? And this is the output that we have created, right? So let's print the output also. I don't need to print this too because these two we are using anyway. Yeah, so the output is finally 9. Okay, so after all this thing, we have got an output 9, right? Now, two things are missing here, as I think Shruti mentioned. So one is the bias. We have to add the bias. One is we have to add the activation, right? So let's add the activation first. So bias is essentially like I discussed yesterday. So bias is essentially to move the activation function to the left or right. So bias is not that important, right? And when we actually see Keras or TensorFlow code, bias is anyway a parameter, right? It's W0. It's a parameter, so it will randomly get assigned, right? And it will be assigned and optimized. Okay. So now let's try to add the ReLU first, and then we'll think about the bias aspects. Okay. So before adding the ReLU, so what we talked about, so this multi-add process is only the half the story, right? So for adding neural networks to achieve the maximum predictive power, we must apply something called the activation function, right? So what is the activation function? So activation function allows the model to capture the non-linearities, right? So non-linearities like we had seen yesterday, so it can be like capturing patterns, like how say going from no children to one children may impact your banking transactions differently, right? Than going from 3 children to 4 children. So that is a non-linearity, right? Or another non-linearity can be like say like you weren't retired, your bank balance was different. Now you're retired, your bank balance will be different, right? So that relationship. So for all these, we need to add activation functions, right? So an activation function is something applied to the value coming into a node to to change their outputs, right? So let's write it down actually. So what is an activation function? So an activation function will be, I can use maybe a markdown. To markdown. Yeah. Yeah. So an activation function is something that yeah, an activation function is something that helps us that is applied to the value coming into a node, right? Which then transforms into the value stored into that node or the node output, right? So let's add the activation function for this problem. Okay, so now we have the basic data. So when we add an activation function can be used at every layer, right? So we can define it as a function, right? We don't need to like write it at every point of time, right? So for now, because I have to implement it, I'm going with a very simple activation. Okay, very simple activation. So I am going with a say a ReLU kind of a activation function. Okay, so let's try to do that. So let's try to
We can
create.
use any kind of activation, no? Not only this rectified linear, but
You
other.
can use any kind of activation function. You can use tanh, you can use sigmoid, right? Anything is yeah, any kind of activation function is fine.
Okay.
I'm just going with ReLU, yeah, because it is very easy to implement. So you can use anything. So there are standard functions in NumPy. You can apply sigmoid. You can apply these kinds of functions.
Okay.
Right? Yeah, yeah.
I lost the half screen. I'm not sure why. Okay, got it.
Okay. Yeah. So yeah. So let's try to add the function then, the ReLU function. Right? just define the ReLU function. Okay, so ReLU is one of the activation functions that we had looked at yesterday in the theory aspects, right? So what ReLU does is it takes the input and what it does, we had seen that the output is nothing but before 0 it remains 0, after 0 it becomes the input only, right? So we can just do max of input and 0. Okay, so this is the ReLU function and then it returns the output, right? So this is the ReLU function. So this I am keeping it defined separately. This I'll call at every point of time to use it. Okay, so where all will I be using the ReLU function? So I'll be using at, so where I have created node 0 value, right? After the value, the ReLU will be added, right? After we add the dot product, then we'll add the ReLU function. So we'll just call it node 0 input now instead of node 0 value, or I'll just copy this actually. So this is without ReLU, right? So let me copy this and then I'll apply the ReLU function here. So I'll just call this as node 0 input, and node 0 output will essentially be, can anyone tell what will be the call to ReLU function for node 0 output?
Sorry, what was the question?
Okay, so the question is, no, this is the input that will go to node 0, right? This
Yeah.
we have seen.
Hmm.
Earlier, this input used to be the output only because this was directly going to the hidden layer. Now we have to apply a ReLU function on top of this input, right? So the question is like what we will add as the node 0 output. So it will take something as input and give something back as output. So what will be that output?
We should use the ReLU function.
Correct. So we should use the ReLU function. So we will just pass this to the ReLU function. Right? Now what we do, now everything similar thing we will do at node 1. So we'll just call this node 1 input, and this I'm just calling it so that it's easier to relate. Okay. Then we have the node 1 output, which will take the node 1 input and then hit the ReLU function on top of that. Right? Then these two ReLU functions will go to the hidden layer, right? So what two things will go to the hidden layer now? Hidden layer will have node 0 output because that will be the input to the next layer, right? And node 1 output. So now directly the values or the inputs will not go, right? After we have hidden the ReLU function, then we will be passing this, right? So we can also try to print these two things. So we will also try to print node 0 output, and we will be printing the node 1 output here. Okay, and then we'll be printing the hidden layers of hidden layer values also, right? So we have the hidden layer values, right? These hidden layer values has to go to the output layer. Okay, so once they go to the output layer, then the output layer again is a perceptron, right? So the output also will have a hidden layer. So we will call it, say, so we have the hidden layer inputs. Okay, this is the output layer. So this the final layer, it is just the output. So we don't have a second layer here, right? This is just the output. So the output will not need to have a ReLU here, right? Because this is not a perceptron in itself. It is not changing the data. It is just the final data that we are getting by combining the two hidden layers, right? So we are just doing this, and at the end we are just doing a dot product, and we are trying to print the model output. So let's call this model output. Okay, and we are just trying to print the model output here. Let's print this. So we see that we had node 0 output was equal to 5. Node 1 output was equal to 1, right? Then hidden layer values was 5 and 1 because that's just a combination of node 0 and node 1 outputs. And then we join the two outputs to make it 9, right? It is same as this, because it's a ReLU function. So if nothing is negative, then it is equal to x only, right? So we don't change, nothing got changed, right? So if I had a very big negative value, then some things might have been negative, right? And then you will see differences in the two outputs. So if I change -1 to -5, then you are seeing, without ReLU, you are seeing an answer of 17, right? With ReLU, you will see an answer of 10, right? Because ReLU function, for the negative parts, it just changes it to 0, right? It's a linear activation function. Okay, it's a non-linear activation function, but the parts of it, the differentiable parts of it are linear, right? So this is a basic implementation of the ReLU function and these things. So you can maybe, if you want, as an assignment, as a homework, you can try to implement a sigmoid function, right? So I'll not write the code for sigmoid function, but you can just try to fill in the blanks here, like code for sigmoid kind of thing. So this will essentially help you to understand, okay, how sigmoid is implemented in Python. And then you can return the output here, right? And you can call the sigmoid function instead of the ReLU function in all the places, right? So this you can take as a small assignment that you can do. Okay, so questions. Any questions, anyone?
So what do we call as a perceptron? It's a node.
Yes. So each node is a perceptron, correct?
Okay.
So any node that is there, that is a perceptron. A perceptron has two parts. The first part is this joining and adding, this multiplying and adding, the dot product. The second part is the activation function, right? So here, if you see, here this node 0 and node 1 were our perceptrons. This output is not a perceptron. This output is just combining node 0 and node 1 with some weights, right? The output is not a perceptron. The output is just a combination of node 0 and node 1 with some weights. So that's why at the end, we don't have a non-linear activation function, right? So we are not calling ReLU on top of the hidden layer model output. Okay.
So when you said ReLU is a linear function with non-linear.
No, ReLU is a non-linear function. Obviously, it's non-linear because if you see the graph, it's not a straight line, but it has linear differentiable parts. I'll come to that. I'll talk more about it in the one more. But is the code clear for now?
Okay, if we in the output, if you have two output, right, then we need to apply ReLU in the hidden layer also.
Yes, so the model output will only be a 1. So each model can only give only one output, right? So if you have two outputs, that means it's a hidden layer only. It's the second hidden layer. It's not an output layer.
Okay.
Right? And because it's a regression, it's a plain prediction model. So at the end of the day, you have to give out a number. So if you have two numbers, you have to again push it to a third layer with some weights, again a ReLU, and then finally get the output.
Okay.
I'll share all these notebooks and everything, so you don't need to write the code per se for now. So I'll just to answer both the questions, like for the differentiation part and this part. We'll switch back to our notebook a bit. So the ReLU function essentially looks like this. Okay. So ReLU function looks like this. So before 0, it is 0. After 0, it is x, right? And that's why we write it as y equal to max of x and 0. Okay, so this is the ReLU function. So these two individual parts are differentiable. These two linear parts are differentiable because y equal to 0 is differentiable, y equal to x is differentiable. The differentiation of y equal to x is dy dx equal to 1, right? If you remember your calculus days. So both the parts are differentiable. Okay, it is not differentiable at 0 because there is a sudden change, sudden edge change. Where it will be important will come when we talk about backpropagation. We'll see why it is important. Okay, we'll see why it's not being differentiable at 0 makes a problem. Okay, so Yeah, please go ahead.
I'm having a doubt why we are not applying the ReLU function for the output one. Only when we apply the ReLU function to the output one, it will get activated, isn't it?
So
In the
ideally, we don't want to. So this output essentially is not a node anymore. So only these parts are the nodes in this diagram. These are not your nodes. These are your inputs, right? Input one and input two.
yeah,
This
exactly.
output, essentially, this output, what it does, this output is not uh, creating anything for the next round, right? So the why we need the ReLU function, why we need an activation. We need something to be activated so that the next layer does not get a linear answer from the previous layer, right? Because if I only just made some linear change and passed it forward, then essentially I did nothing. That thing that next layer could have done, right? But for the output layer, there is no next layer to pass it to, right? So you don't need to worry about having a ReLU here. You can as well have a ReLU here, and it won't matter much. But say if you had a negative prediction, right? If your answer, the final answer would have been negative, it can happen, right? Say you are trying to predict, say, some cash flow of a particular company, which can be positive or negative, right? I did not take the number of transactions example because that cannot be negative. But cash flow of a company can, not cash flow, but say net profit. Net profit can be negative. Now, if net profit is negative, but you apply a ReLU function here, then for every negative value, you'll be predicting 0.
Yeah, exactly.
Right? So that's why we don't apply a ReLU function at the end.
Okay.
Because your output could easily have been negative.
Yeah.
Right?
Even in the
So,
hidden layer also, we shouldn't apply ReLU over there.
Hidden layers, you can apply ReLU. Hidden layers, you can apply ReLU because we'll see that. We'll come to that when we look at
No.
backpropagation.
In the example which you gave now for the negative values.
No, negative values, maybe hidden layer pe you can apply because the other parameters will get impact because when we actually do the weight, when we actually modify the weights, right? So here to be hard coded the weights and move things forward. So we looked at a forward propagation. So this is known as the forward propagation. We went this side.
Okay.
Right. So there is generally another concept that we'll talk about mostly tomorrow that is known as the backward propagation. So when we come back, okay. So when we come back, then the negative values will automatically, the model will automatically try to change them. Right. Obviously, ReLU will give a 0 output for negative outputs, but the weights will get changed accordingly. So, and then the final output, you will see it will go very close to the actual output, right? The prediction, and you will see the mathematics behind it. We'll see the gradient descent algorithm and why it will always happen, kind of thing. Okay, but the output layer, you can never apply an activation function for these problems, right? There are other problems also. So if you did not use a ReLU, and this problem is not related only to ReLU, is what I mean. So if you had something like, say, sigmoid, then you would find a similar problem happening. So sigmoid function basically looks something like this, if you remember from yesterday's discussion.
Yeah.
So sigmoid always lies between 0 to 1.
And 1.
Right? So if this is R1 and this is R0, this is the two axes that we have. So sigmoid essentially looks like it starts from here and it hits here and it goes here, right? So it will look mostly like this. Right? So whatever be your output, if you're doing a regression problem, you say your output is, say, 5,000 crore, the business will do 5,000 crores today. Your sigmoid function will make it to 1.
Yeah.
Right? So it will not add any value. You will get outputs between only 0 and 1. Right? It might add value. Where it might add value? In classification problems. So we'll look at that. So we call it a softmax activation layer that we add at the end to make it between 0 and 1. That is the same thing we do in logistic regression. Right? But in a regression problem, where we are predicting real numbers, you cannot apply a activation function at the end.
Yeah, okay.
Okay. So yeah, any other questions from the things that we looked at?
Suppose like if we are going to add one more hidden layer, so from where the values, we will be taking the values of the hidden layer 1 to hidden layer 2, or from the input we will be taking it.
So you will take it from the hidden layer 1 only. You cannot take it from the input because if you say that there is a hidden layer here, you can see the diagram, but you are taking from the input, that is essentially these two nodes are here only in the first layer.
Okay.
Right? So you cannot have a hidden layer from the input after the first hidden layer. It has to, it essentially means they are here only, because the first hidden layer they are not actually impacting the second hidden layer, right? So the second hidden layer is nothing but your first hidden layer only. So they can be
Okay,
merged.
so what will be the
essentially.
maximum hidden layer we can have?
Generally 2 to 3. Generally, even in large language models like say ChatGPT and all, use like maximum 4 hidden layers kind of thing. Okay, maximum 4 hidden layers. Just that their number of features are very huge.
Okay.
So you are vertically, the model will be very huge. Horizontally, the model won't be that long.
Okay, for this one hidden layer itself, the model will be very huge. That is what you mean to say.
Correct,
Okay,
correct.
okay.
Yeah, and they have like we'll look at other types of neural networks also. So other types of neural networks generally, like I'll not complicate things, but right now because we are just beginning to read about it. But like textual models, when we look at, we'll see that this node will also fit to this node in the same layer. You will see this node feeding to this node in the same layer. These we call as recurrent neural networks, right? So same layer, there is communication between them, not even in the next layer. So that makes very difficult things, that makes very difficult optimizations and things like that. But we'll come to those. We'll talk about those, but not at this moment.
Okay.
Okay. So this is what we have right now. This is what we discussed, right? So we have the basic forward propagation up. We have discussed the ReLU. We have discussed the how to code it up and how to build the logic behind it. So we have the model outputs now with ReLU. So the other part is, right, one question might come, that is like this we have done for one layer, right? This we have done for one data point, right? What will happen if there are multiple data points, or what will happen if there are multiple layers, right? So let's take a look at first multiple layers, and then we will look at multiple data points. Okay. So if I have to have a multiple layer thing, then say something like this, I will try to build, say the multiple hidden layer kind of thing. If I'm trying to build, then I will have, say, again, 2 features. In the same topic, we'll try to cover both. One is multiple data points and one is multiple hidden layers. Okay. So say we have a first hidden layer here, second hidden layer here, and the final output. Okay. So this to go here, this to go here, then right? So if I have to just add the weights, I'll just change the color and add the weights now. So say 3 and 5 are the initial inputs. Okay. So say we have 2, 4, and 4 minus 5 kind of thing. These are all random numbers. Okay. And in the next layer, we have say whatever, -1, +1, 2, -2. So say we have -1, +1, 2, -3, whatever. You can keep both twos, nothing, it doesn't matter. Right. And then we have the final output. So how will the code look like? We'll come to the code, but how will we do it? So we'll come here first. Right. We'll come here, we'll do a calculation. So we'll have 2 into 4. So input 1, I'll actually write in the code only, then it will be simpler for me, right? So I'll just go to the code section and reshare my Jupyter. Okay, first of all of you can take a screenshot of this neural network, okay? So that when I write the code, it is easy to understand. And the other part is we will try to add the hidden layer also. So I'm just trying to see if we can add that. Okay, there is some message. Okay, so I'm just trying to reshare my screen. Yeah, so I'll just add now a new layer here. So we can use the same function, right? We can use this same thing. We'll change the weights, right? So we can So generally the nomenclature looks like the first earlier we had 0 and 1 only, right? Because we had just one hidden layer, but now there are two hidden layers. So it becomes very difficult to like look at like what hidden layer, where the node and all these things, right? So we have to make it correctly. Okay. So what we have to do is we have to make it correctly. So we have to name it correctly first. So let's do that naming convention first. Okay. So we'll call it node 00 and we'll call it node 01 for the first hidden layer. Okay. And then for the second hidden layer, we'll call it node 10 and node 11. Okay. So we are giving the hidden layer number first, and then we are giving the node number in that layer. So let's try to do that. So what were the weights we had kept? We had kept 2, 4, 4 minus 5. Let's put them first. So we had 2, we had 4, 4 and minus 5, 4, 4 and minus 5, right? Then we had, similarly, we had, I think, minus 1 plus 1, 2 and 2, right? So we had minus 1 plus 1 and 2 and 2, right? These were the input, and then the last layer, the numbers I forgot to write there. So you can assume that it is say minus 3 and 7. Okay. So the last layer again will have two weights that I forgot to add in the diagram. So it will be minus 3 and 7. Okay. Again, these are just random numbers. Right. So with this now, if I have to build the neural network, how it will look like? So we will not say node 0 input anymore. We'll call it node 00 input. Right. And we have the input data. We'll create the sum. So we'll adjust these names accordingly. Right. Again, then we'll call it node 00 output. Right. We'll call it node 00 output, and which will basically be a value of the node 00 input. Right. And we will just create the print. We'll just print this. Okay. So this thing now we can copy and use it everywhere. We can just paste it 3 times. Right? Why? Because it will be node 01. That is the first hidden layer that we'll look at. Right? So node 01 will look like this. It will, right? Now, node 10 will not be looking like this directly, right? It will not look like this. Can anyone tell why? What will be the change in node 10? So if you see node 00 and node 01, I have just written it like this.
Input data. We need to change
Exactly.
the
So we
input data.
cannot use input data now. Correct. So we cannot use input data now. So we have to use the hidden layer data kind of thing. Right. So we will just take this and we will call this as a hidden layer 1, 0 kind of thing. Right. Or because we have two things only. Yeah. Hidden layer 1, 0. And this will have node 00 output and node 01 output. Right. Similarly, and this hidden layer 0 essentially will become the input data here. Does it make sense, everyone?
Yes.
Okay, great.
No,
Similarly, can you repeat? I didn't.
No, so can you go back to diagram?
Yes. I'll go back to diagram. Yeah, I'll go back to diagram. Give me 1 second. I'll just check if I can add a here. I'll figure that out. Actually, if there is a chance that we can add the diagram also here. I'll figure it out. Yeah. I put the diagram up. So yeah, please go ahead with the question.
Some basic questions. So
Yeah, please go ahead.
when you're talking about node 5, 4 and minus 5 are the inputs, or what do you call that?
No. So these two are the inputs. 3 and 5 are the inputs. These are not nodes. So okay, these are not nodes. These are the inputs only. 4 and 5, -5 are the weights to this node, are the weights of the edges.
Okay, okay.
Right? So these two are getting fed, these two are getting fed. Right? So whatever the output comes here, this is called the hidden layer 0, 1 or hidden layer 1, 0 kind of thing.
Okay. Got it. Fine. That's what I was. Okay.
Yeah. So this is what I wanted to explain. Okay, this makes sense, everyone? Great. So a similar thing. So now we can just handle for the other
Can a
layer
weight be
also.
negative?
Weights can also be negatives. Yes, weights can be any value, random value. Okay, weights are any random value. Why? In a practical scenario, when a weight can be negative, when a number is inversely proportional to the output. Right. So as your age increases, your salary increases. So it's positive. But maybe after 60, your salary decreases. Right. So it's an inverse parabola kind of thing. And after 60, if you have to just model that data, it will be a negative. So as the age increases, the salary might decrease. Right.
So, got it. And when you're
Yeah.
talking about hidden layer, these two hidden layers, or I don't know why I call
Yeah.
it
So
hidden layer.
in this problem, we have two hidden layers.
Yeah. So why you call it hidden layer? No issues. But in that cell layer 1. So we just don't add hidden layer, right? It should be doing something. So that's where I started doubting myself why we are adding it, or just for sake of. Means if you go back to this diagram. Can you go back to the diagram?
Yeah.
Just a
I'm on the
second one.
diagram.
Second one.
This
Second.
one.
What is this one?
Yeah. So this one also we are adding non-linearity, right? We are though the inputs. Yeah. Now the inputs are different. So what are the inputs here? So if you see the inputs are 6 plus 12, that is 18, and then some value. So what I'm doing is 2 into 3 plus 4 into 5, that is 26. Okay. So 2 into 3 plus 4 into 5. Here what it is? Here it is minus 5 into 5, that is minus 25, plus 3 into 12, that is 12, that is minus 13. So once you apply value, anything negative becomes 0. So this is 0. Right?
That's what I'm saying.
So here what it is, here what it will be 0 into 2, that is this
0.
line, plus minus 26 minus 1. Correct. So minus 26 makes it to 0.
Yeah.
Here what will be? Here it will be 26
Same.
into 1 plus, no, this will be 26 into 1 plus 1 plus 2 into 0, that is plus 26.
26, yeah.
Right?
Fine. But okay, if you take this 0.26 out, directly move to the output, the output will be change.
If you take 0.26 out directly, then basically you don't have this hidden layer anymore. Right? And you are just passing, say, 26 into minus 3 plus 0 into 7. So the output becomes, minus 84. Minus 84 only, right? 78, sorry.
78.
So the output becomes minus 78. This one. Because there is no relief here. We discussed this before, right? But with this, what is the output? With this, the output is 26 into 7, that is 140, 182. Right? Minus 3 into 0, that is 182 only. So the outputs are different. So the moment you added a hidden layer, the output changed. Right? I'm not saying that one is correct or one is wrong. Right? Because these are all random numbers that we have taken. So we don't know the correctness yet. We have not trained the model yet. We are just looking at the forward propagation layer for now.
Okay, got it. Thanks.
Okay. Yeah. So note that I am not talking about whether 182 is correct versus whether minus 78 is correct. There is no correct or wrong here, right? Or I can say both are wrong, because neither of them have been tuned yet. The model has not been trained yet. We have not seen the actual data yet, right? We are just looking at the parameters and we are trying to predict something with the parameters. We are not seeing what should be the ideal value or what is the actual value with that parameter. So we are not looking at training data yet. Okay. So this is the So we are not saying that 182 is correct or minus 7. If you added another layer, the answer would have been something different, right? Generally, we have seen that adding after 3 layers, generally the answers don't change much, but not these answers. The first iteration answer will be different, right? After you do 2-3 iterations of forward and backward propagations, so we'll generally do a backward propagation, then we'll do a forward propagation, then we'll do a backward propagation. So after doing it 2-3 times, you will see that the number of layers don't matter much. Okay, so we'll come to that, why it doesn't matter. We'll talk about what happens in the backward propagation in more detail. Okay, so yeah, so what I was saying, I was going to the code. So yeah, now basically, similarly, you can implement the hidden layer parts, right? So one is the hidden layer 1 that takes the input from node 0, 0 and node 0, 1. Then you will have hidden layer 2 also. You will have hidden layer 2 also that, so this is hidden layer 1. So hidden layer 1, you can multiply by the weights of what will you node 1, 1 and node 1, 2 kind of thing, right? I'm not writing the code here, but this is like iterative. Okay, so I have to put the code. I'll just see if I can put the code. Okay. Yeah, I'm just adding more comments and putting the code. Okay. Yeah. So we have node 0, 0 input. Then we have the, I'm just adding the comments I put just to like show that, like, so that you don't get confused, right? When you actually look at it after some time at home, like after 2 days, if you revise it kind of thing, right? And that is how we are calculating it. So we have hidden 0 inputs, outputs. Then we have the hidden 1 outputs, which is going to the final output. So we have 2 layers now. Okay. So this is what we have. Note that this we are doing for only one data point, right? So that is now the catch. So a training data, when you will have some millions of data points. You will not be doing it for only one data point, right? So what we will have to do is you will have to take it as a function and do it for each data point. So this part that we did, we will create a function for this. So this is for say one data point, and this is fine. But if I have to actually write it production code, I will have to create a function for this one, right? Because each data point has to go and hit this function, right? So say I'm calling it predict predict row. So each data point or each data row that we call, right? And we have say input data. Okay, so this is a function. So the function signature, so this will get indented, right? And this is the function that we have and the model output that we have. So we'll be returning the model output from here, right? We'll be returning the model output from here. So this is a function that I've created. Okay, everyone got it, what we did? So we created a small function here, right? Which just does all the things that we discussed for one row, right? It does all the things that we discussed for one row. So now it will just be that you are calling this function for the whole input data, right? So you are just calling this function. So say you have a very big training data. So I will just write for input data or for input data in training data. Training data might be like a combination, a lot of input data, right? Lot of rows are there. So here, what I'll do is I'll create say a training result kind of thing, right? Training result kind of thing, which will have the result of the forward propagation for each training data point. So I'll just pass this. I'll just call pass predict row for the input data, right? And I cannot do this equal to, so I have to append it. I have to append this one. Does this make sense to everyone? Any questions
Training
here?
results should be an array, list, empty list. Only then we can append, right?
Training result is an empty list. Correct. Okay. So we have seen forward propagation in a deeper layer, and we have seen the levels of representation, right? We'll talk about how the different representations are learned. Okay. So I'll just create the empty list part that thing should be told. So yeah, so we have an empty list and we are just saying that input data row, we are just calling it with the weights. Obviously we have to pass the weights here, right? So I've not passed the weights here. So let me pass this. and the weights are, say, hard-coded. Weights you have already hard-coded once, right? So instead of input data that we had one row, now we have many rows, right? So this is essentially one forward propagation of a neural network. Okay. So I'll just, yeah, there is some error. What is the error? Okay, predict with network. I think my name is, I call predict row. So let's call it predict row. Yeah, perfect. So once you do it, you get this as an output. So basically I had if I had, say, like multiple input data, then I will get multiple outputs, right? So this is what I wanted to discuss. So now tell me any questions, anything anyone has. I'll share the notebooks and everything in the Google Drive location only. Okay. I'm not sure if the lectures recordings are shared. So, but let me know if you have any doubts with any concepts. I'll again explain it in the next class. Right.
So output we need to get one value, right?
But this is for one data point you need to get one value. This is multiple data points. So input data now has multiple data points. Right. So input data has like an array of 2 and 3, which are two. Essentially, we are doing it for each data point now.
Okay.
So for 2, we are doing it. Then for 3, we are doing it. Right. Yeah. So for each data point, you need to get an output, right? Because say you had 2% transactions. You want to like A, you had some data, B, you had some data. So for A, you will want to predict, for B, you will want to predict, right? And then you will check the errors. And then you will try to tune the model. So we have just seen one iteration now. So tomorrow we'll look at optimizers, and backpropagation. Okay. So I'll just save this. I think this is saved. So any other questions, anyone, before we wrap?
So
Can
if
you
we
please run
use
the above code?
Which code?
This one. Yeah, 19th. Yeah, this one. What is the result? We'll get that.
This is just a function. This is just a function, Shivraj. So
okay.
yeah.
Change
with the 2 hidden layers.
Okay.
Okay. So earlier we had seen it with 1 hidden layer, so I did not run it with 2 hidden layers, kind of thing. It is the same thing. We are just trying to extend that learnings.
Okay.
Yeah.
And like if you do it with sigmoid function, it should be between 0 and 1, right?
Not the final outputs. That's what we discussed. So the intermediate hidden layers will have 0 to 1, but not the outputs. Yeah, if you see here, the output is a square. So each circle has 2 parts. Say the hidden layers are circles. Okay, each circle has 2 parts. One is the dot product and the sigmoid, the activation function.
Yeah.
The output layer only has the dot product. It doesn't do the activation function because you can have any value ranging from -infinity to +infinity.
Yes.
Okay.
I got it.
Yeah.
Got it.
Yeah. Okay. Cool. Then I think, yeah, this is more or less what I wanted to discuss. So if there are no other questions, we'll wrap today. Okay. So tomorrow, again, very important day. So this first week will be very important in terms of setting the context. So tomorrow we'll look at optimizers and back propagation in a bit more detail, right? So we have today seen the forward propagation. So tomorrow we'll look at the back propagation and take it forward from there. Okay. So thank you. So if there are no other questions, we'll wrap. Yeah. Thank you. Bye.
Thank you.
You.